Hey guys, welcome back. I hope you had a wonderful Christmas break. I enjoyed my time off, but I got bored and I'm really excited to be back, especially because we're in person and I feel like we're probably going to be in person for the rest of the year, which makes me so happy. Yeah, so things are good. If you are continuing with distance learning though, I'm still going to be making these videos. This video is going to be done the lectures actually be done in person. So if you are in person, you don't have to watch this video, but I'm still making the video for all of you guys who are staying home. The few of you who are staying home continuing with distance learning. So I'll still be doing these like I did before, which just means that I got a lot of work to do, but it's okay. So I'm still your teacher, even though I won't be able to see you for the rest of the year, which is really sad, but that's okay. I'll see you next year, I guess, maybe, unless you're a senior. I don't know. It's really sad. Anyway, but I'm still your teacher. So if you need any help, please let me know. I can still do private tutoring through Google Meets, or if you're not satisfied with your grade, just talk to me. We can see if we can redo tests, do a tutoring session, something like that to get your grade up. So anyway, they also extended the deadline for the grades through January 22nd. So if you turn in any homework from the first semester before January 22nd, you got to give me enough time to grade it though. So, keep that in mind. I'll get it graded and then your grade will go up, which is kind of nice. Also, I dropped the lowest test score and stuff like that. But anyway, if you have any questions, just hit me up and we'll go from there. So we're going to move into probability. This sounds, you would think like statistics is a lot of probability, and it is, but this is probably one of the harder units that we're going to get into. I really enjoy it. I think I've gotten better at teaching it. Hopefully I've got really good visuals and you guys will do just fine. But we'll see. It gets better every year, so this year will be even better. So first thing is we use probability informally all the time in language, like even all the time. What do I mean by all the time? Like 80% of the time, like 80% of conversations. You get the idea, right? So if I ask a question of how often do you get a green light? Well, do you never get a green light? Do you always get a green light? Most often. So these quantifiers, they're really, we're talking about probability, but this type of probability, it's not based on it's subjective. It's based on your feelings, right? So this would be what we would call personal probability, and this is not the kind of probability that we're going to be dealing with. We can't really quantify it in that case because it kind of changes based on your opinions and stuff like that. So instead, we're going to be dealing with theoretical and empirical probability instead of personal probability. So if we did want to quantify this instead of just going off of our gut feeling or whatever, so like if we said, if we never get a green light, then the probability of getting a green light, and this is kind of notation we use for probability, kind of like a function, like function of x, but it's the probability of g, which is event g, which we're saying is green. I don't know. So if we never get a green light, then the probability of getting a green light, we're saying it's 0. We can't go negative, but the lowest that we could have would be a probability 0, or 0% of the time, right? The highest probability, so if we always get a green light, we're just super lucky, right? Which would be awesome, but it's never true, right? Then the highest we could ever get would be 1. So we don't do like 100, like 100%. We're just going to do 1. So it's strictly, the probabilities of any event strictly between 0 and 1. That's kind of like the first rule of probability. All right, this again is personal probability because it's subjective. It's based on your personal degree of certainty, which again, we can't really quantify. If I had to estimate what percent of lights that I get, sometimes it's over 50 and sometimes it's less than 50%. So most of the time it's probably 40% because there's light traffic, but it just depends on the time of the day, right? Stuff like that. All right, so the first rule is that the probability of any event is strictly between 0 and 1. Can't be more than 1, can't be less than 0. So yeah, probability of an event strictly between 0 and 1. That reports the likelihood of the event's occurrence. We write the P of A, the probability of A, for the probability of event A occurring. And this is from page 345 if you want to look it up in your book. All right, so if it never happens, then the probability is 0. If it always happens, the probability is 1. And the probability of event G is going to be somewhere in between 0 and 1, strictly speaking. All right, so exactly how often do you get a green light? If we want to go beyond our subjective personal level of certainty, which is personal probability, which we don't deal with, then one thing that we might do is we actually record the amount of times you hit a green light at a certain intersection on your way to school. So let's say you pass by MacArthur and 50th on your way to school every day, right? And every day you come to school, you record whether or not that light was green, or if you had to stop at the light, if it was red or yellow or whatever, and you ended up stopping at it. And you just record this for the whole school year. So you got 180 days worth of data, you graph it all out. Then we could actually see some kind of beautiful stuff if we spend the time to do all that. But we're going to do simulation, so we don't actually have to do anything like that. All right, moving on. So exactly how often do you get a green light? Light is on a timer. So let's say it's not based on like sensors, but it's based on a timer. So for instance, it might be based on the time of day. So at 7:15, that light is always green. I'm pretty sure it's based on sensors, but it could be based on a timer. And if it was on a timer, it wouldn't actually be random. But what is random is what time you arrive at the light. So you don't, unless you strictly leave the house at the exact same time and all the lights going there are all on a timer, then possibly you could time it so that all the lights were green. Wouldn't that be magical if we could like develop a utopian society where if you were like a part of a group of people that you like traveled in a tight pack, like a pack of wolves, and you could like time it where all the lights would turn green and you never have to stop. I've actually thought about these things, but instead I became a math teacher so I can tell you about these things. It's fun. All right, so when you arrive at a light, that's actually going to be truly random because you don't always leave at the same time, and whatever events occurred before you got to 50th and MacArthur is going to be different. So there is the random aspect here, and this will be what we call a random phenomenon. So our trial is each time we observe a random phenomenon, the outcome is the observed value, so whether or not you had to stop if it was green or not. All right, so day one, you got a green light. So far, the cumulative relative frequency is 100%. So far at that point, you could say, every time I've seen that light, it's been green because we've only been recording from that part. All right, the second day you got a red light, which so now our cumulative is now going to be 1 out of 2, which is 50%. Day 3, it was green again, so that's 2/3, right? So 66.7%. Then it was green again, 3/4, then red again, which would be 3/5. I don't know, this thing is down on me. Or 60%, and then red again, and went down to 50%, and then it's going to fluctuate all over the place. Now, if we look at this chart here like we did before in Unit 1, I mean, if we just kind of read down this line, we can see what's happening. It's actually better to read down the line and see the cumulative numbers instead of just seeing green, green, red, green, red, green, green, green. We'd see a lot of patterns. Maybe there were 3 greens in a row, which would be unusual. But what we really want to know is this cumulative relative frequency, and where's the number going? It started out at 100. It's not going to stay there. But where is it going to go? And so what happens when we graph this out as a scatter plot, we get this beautiful thing. Isn't it amazing? And we can do simulations. In fact, there's plots that I created from our graphing calculator, and I'm debating whether or not we're going to do it in person. Depends on in class. Depends on if how long this video goes, really. And I'll probably split out into a separate video to show you how to do it on your graphing calculator because it's going to be pretty legit. And something that if it's a smaller video, people just prefer that. So we started out at 100, then went down to 50, and then went to 2/3 and 3/4 and back down to 50, etc. Blah blah blah. Bounces around a bunch, passes below this 35. But eventually, what happens is you have convergent behavior. So if you're in calculus or if you took calculus, you talk about divergent and convergent behavior really in Cal 3 or whatever, but you even get that before that with limits, like as approaching infinity. So as we keep going on and on and on, eventually this is going to settle down to something called the empirical probability. So the empirical probability is it's not based on like a theoretical probability because it's observations of a random phenomenon, but as we do a large enough like sample size or we do enough trials of our simulation, it will actually settle at a certain number as we go, as we increase the number of trials to infinity, which is the law of large numbers, by the way. It will approach a number if the events are independent. So if having green light today does not change the probability of having a green light tomorrow, et cetera, et cetera. So if they're truly independent, then there will be an empirical probability, and we can actually figure out what it is based on doing simulation, which is cool. So the relative frequency is going to bounce down, and eventually it'll settle to, in the long run, empirical probability, which is cool. So if the empirical probability of event A is 35%, which is the event that it's a green light, then what's the probability that it's not going to be a green light? Like, what's the probability it's going to be a red light? Well, it's actually going to be 1 minus the 0.35, which would be 65%. So 65% of the time, you have to stop. Now, whether that was a yellow light that made you stop or it was a red light itself that you actually stopped for, then anyway. All right, so what about a yellow? Well, we can treat yellows as a red or we can treat yellow as a green. So if it just turned yellow and you can't safely stop without like squealing tires, then you just need to like keep going. But sometimes, you just like see yellow and you like slam on the gas, not the brake. You're like, oh no, I didn't know what pedal. Anyway, I'll let you guys figure that out, and hopefully, yeah, just drive safe, please. All right, so sometimes it's yellow and we go, and sometimes it's yellow and we stop. If it's safe, if you can stop, you probably should stop, unless somebody's tailgating you and you don't want to get ran over. But all right, so anyway, we can treat it like it's a green light or a red light. We either stop or go. The trial is each observation of the random phenomenon. The event is going to be whether or not it was red or green. Basically, did we stop or did we go? The outcome is the observed outcome of the random phenomenon. Was it red? Was it green? Or was it yellow, I suppose? And the sample space is a set of all possible outcomes. So this is really important. So like think of space like the final frontier. It's like everything, right? So the sample space is the set of all of our possible samples, which is all the possible outcomes in this case. So our sample space, which is denoted capital S, and then the brackets here, and these are going to list off all the possible outcomes. We could have a red light. We could have a yellow light that we treat as a red, meaning we stopped at it. We could have a green light. We could have a yellow light that just turned yellow, so we went, so we treat it like a green. Okay, so there's 4 possible outcomes when we're driving. There's not a 5th one that I know of. Oh, stop sign. That's clever. You always stop at sign. Okay, whatever. All right, we toss a coin twice. So what's the sample space for tossing a coin twice? So we could get 2 heads. So the first one was heads, the second one was heads. We could get a heads, then a tails, or a tails, then a heads. So what's interesting here is that the order doesn't matter. So if we're listing it off in this way, it's like a permutation on a combination. So it's not the number of heads we got out of 2, it's the order and of the actual like chain of events as well. Okay, so those are distinct. And then 2 tails, of course, would be the last one. So there's 4 again. Then what are the specific probabilities of those events occurring? So the probability of having 2 heads, well, the probability of having the first one heads would be 50%. Then the second one, because they're independent, it's still going to be 50%. So 50% times 50% is actually going to be 25%. Oops, didn't mean to do that. So there's actually a 25% chance of getting 2 heads. Heads and a tail is still 50 and 50, so it's still 25%. I'm struggling today. And then heads and tails, it's the same thing, 25%. And then, of course, the other one's 25%. So what's interesting about this one is the sample space is just as likely. All the possible outcomes are just as likely. If we're looking at the permutations, not the combinations. Now, what's the probability that you have 2 heads or you have 1 head and 1 tail? Well, if we're talking about 1 head and 1 tail, then all of a sudden we're looking at this, which is a combination of 2 different possible outcomes. It didn't matter if the head was the first or the last. That would actually be adding these together, which would be more likely to have 1 head or 1 tail than we are to have 2 heads or 2 tails, which would be more rare. So that's kind of what you get into, like with like, let's say that you, like in my family, my parents had 4 girls and 3 boys. So if we're looking at the orders of that happening, that outcome is just as likely as any other order of that happening, or any other like 7 boys in a row, same likelihood, right? But if we're looking at total combinations of all the possible, there's only one way to get 7 boys in a row, but there are different orders of boy, girl, boy, 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 girl, girl, all that different stuff that could give you 4 girls and 3 boys, if that makes sense. So kind of important. And I know that wasn't the best explanation. So does the order matter? If the order does matter, if it doesn't matter, we're just listing it as 2 heads, a heads and a tails, or 2 tails, then now it's going to be 25%, 50%, and 25%. So visually, hopefully you can see there, that's where the difference comes into play there. So then our sample size, our sample space, if we're talking about where the order does not matter, would just be 2 heads, a head and a tail, or 2 tails. And now this one's the most likely outcome, which we'll talk about that with the Bernoulli trials. Yeah, no, not Bernoulli trials, binomial models. Whew. I'll get it down. All right, rule two, the probability assignment rule. So the sum of all the probabilities of the sample space must add up to 1. So if these are all the possible outcomes, the sum of all the probabilities must add up to 1. So that should kind of make sense. We'll see some examples that should help that. All right, so sample space number 2. So for all the following, list the sample space and tell whether you think the events are equally as likely. All right, roll 2 dice, record the sum of the numbers. So you could get snake eyes, which would add up to 2. They could add up to 3. They could add up to all of it. The highest they could add up to would be 12. So all the numbers from 2 to 12. You don't have to write them all out. You can use the ... there. All right, do we think those are all going to be equally as likely? We've actually shown this one before. It's the triangular distribution, if you remember that. The most likely outcome for the sum of 2 dice is going to be 7. The rarest, of course, is 2 and 12, because there's only one combination of those dice that can give you that. So, but there's actually 6 combinations. So whatever you roll for the first dice, there's always another roll. There's always one possible outcome from the second dice that would make it add up to 7. So that's why it's 1/6. Anyway, kind of cool. So they're not going to be equally as likely because there's multiple combinations to be able to roll a 7, where there's only one way to roll a 2 or a 12. Our family has 3 children. Record each child's sex in order of birth. So if we're talking about the order mattering in this case, so we could have, I'm just going to list them off. So 3 boys, boy, then a girl. So the girl's the oldest or the youngest, the girl's the middle child, or the girl's the oldest. And then the same thing could happen with 2 girls and 1 boy, and then all girls. So those are the outcomes. So the probability of having 3 boys is 1 out of all these combinations. Probability of having 3 girls is 1 out of that. Same thing with like the dice here. It's actually kind of cool, and it's all binomial theorem here. And then we have 3 combinations of 2 boys and 1 girl, and the same thing, we have 3 combinations of 2 girls and 1 boy. It's the same thing, assuming that the probability of boy and girl is 50-50, and it is. All right, except there are slightly more females born than males because I don't know why. Biology. Mysteries. All right, toss 4 coins, record the number of tails. So we could have 0 tails all the way up to 4 tails. So those are all the possible. And are they all equally as likely? No, the middle ones are going to be more likely than the rarest, which would be all 4 tails or all 4 heads. All right, toss a coin 10 times. Record the length of the longest run of heads. So we could have no heads, which would be all tails, very rare. And then you could have 1 in a row all the way up to all 10 of them could be heads. Again, very rare. And the ones in the middle would be the most likely combinations. All right, law of large numbers. The law of large numbers says that in the long run, the relative frequency, which is the green part here, of repeated independent events, meaning whatever happens on one event is not going to change the probability of it happening again on the next one. So for instance, like the sex of children. So if you have 3 boys in a row, the next child is still independent of what happened before, and so it's still a 50-50 chance of having another boy or having another girl. It's like the total number of boys that would be, it would be rare to have 4 boys in a row or 4 boys all together, or any combination is just as rare. It's just the total, when you add them together, that's when it's different. Anyway, kind of confusing. And the true relative frequency as the number of the trial increases what it's going to essentially converge to. So where the probabilities of the outcomes are consistent trial after trial, that's what it means to be independent. Then it will converge. If they're not independent, then it won't converge because it's changing. All right, the law of large numbers states that in the long run, it'll converge. So let's say that we flip a coin and there's actually probability simulation. I guess I'll show it to you. All right, so let me show you, I'm not going to show you all of it, I'm just going to kind of show you part of it. But here, if you go to apps on your calculator, and then on the bottom, I'm pretty sure I loaded all of these on everyone's, but the really only ones that we're going to use is probability simulations. And then we're going to do the toss coins. And then these are actually what we call soft keys. And so the buttons here are going to correspond with these soft keys. Okay, it's like touchscreen and anyway, so we have, if we hit toss, that's going to do 1 coin toss, and then we can hit toss again and again. You can do toss 10 of them at a time, you can toss 50 at a time, and then you can clear them out if you want, and yeah, all kinds of cool stuff. So that's the probability simulation. I'm just going to exit. I'll show you more of this stuff later in a separate video. Turn menu, yes, I'm trying to make sure that this is short. Okay, cool. Yeah. All right, so anyway, we can graph out the cumulative relative frequencies as we go. I'll show you that in another video as we flip the coins, and it should approach 50%, right? 50-50, if that's actually a fair coin. So that was the first simulation I did of 25, and even law of large numbers says that as we increase the sample size to infinity, then it will approach that. No, but even with smaller samples of like 25, it might still start to approach it, but it still could get worse. Like, it's not guaranteed to go to 50 and then stay at 50. But in the long run, it will go to 50. That is the law of large numbers. So that was the first simulation I did. Here's the third simulation, I suppose. And then here's the second simulation. So you can see all those. And it does look like even with a small sample size of 25, they are still kind of converging to 50, but again, we're not guaranteed. It could get worse, and we don't know how long until it does converge to it. Just in the long run, we know it will converge. So what about sample sizes of 100? So here's the first one I did to 100. And again, it appears to be going to 50, or at least it's close to 50. Here's the second simulation. Again, that one actually did better, I would say. And then the third one here, that one was too high. But eventually, in the long run, they will converge because it's an independent random phenomenon. All right, what about sample size to 500? So that's getting really close. Like, that's pretty impressive. And the same thing would happen on the second simulation that I did and the third simulation I did. Ooh, except on the third one, it was high and it stayed high. So even 500 wasn't enough to get it to like really converge to 50. This looks like it's converging to something else. So you never really know. All we know, for instance, for the law of large numbers is in the long run, like as it approaches infinity. 500 is a lot of coin flips. Like that would make me really tired. But it's not necessarily infinity. It's not enough. So will it converge? I mean, it's not 80, it's not 90%, it's close to 50, but how far away from 50? There's still going to be some variation there and kind of sampling, kind of cool stuff. All right, so non-existent law of averages. So this is a common misconception. The law of large numbers is true. The law of averages is false. So it's a non-existent law of averages, but it's a common mistake. So common misunderstanding that relative frequencies of independent events will settle down to their true relative frequencies in the short run. So the difference is in the long run they will, but we can't say that we don't know when it's going to happen. We don't know if it's going to get worse at any given point. So regardless of what happens, we cannot predict the short run behavior. So for example, couples have four girls are not due for a boy. So that language, due for something, we don't know what's going to happen if it's actually an independent event. The probability of getting a boy is still 50%. That's just how it ended up happening in the first part there. So yeah, we can't predict short run behavior. We can do long run empirical probability, but not short run behavior. It's kind of like extrapolation. We don't know what's going to happen in the future. So for instance, yeah, we'll do those examples in the book. Well, in the assignment. All right, the non-existent law of averages. So probability of heads, 50%. So we have tails, 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 tails. So what's the probability of heads? Well, we had a bunch of tails in a row. So that means we're more likely to have another tails because clearly the coin is weighted and biased towards tails. Or are we due for a heads? Neither of those are true. The probability of heads, it's an independent event. It's still 50%. It's just, yes, something rare occurred, but that doesn't change. Does the coin remember what it did before? No, that's absurd. That doesn't make any sense. So clearly it's still going to be 50%, right? So in the long run, yes, the overall cumulative, right now it's 0% hedge, right? In the long run, it will approach 50, but we don't know how long it's going to take for that to happen. We could get 5 more tails in a row. That could happen. In fact, any combination of them could happen. We don't know how long it's going to take for it to approach 50%. We know it will eventually get there, but it's going to be in infinity. It will converge to 50% as we approach infinity, but we don't know. It could take 500 before it gets closer. It could get worse after 500 coin tosses. We don't know. So in the short run, we don't know any behavior in the short run, but we do know in the long run, eventually you will get heads. We can say that you will eventually get them, and eventually it'll approach 50% heads, but we don't know how long that could take. Okay, so law of averages, no good. Law of large numbers is good. Long run behavior versus short run behavior. We can't predict it, just like extrapolation. All right, commercial airplanes have an excellent safety record. Nevertheless, there are crashes occasionally with the loss of many lives. In the weeks following a crash, airlines often report a drop in the number of passengers, like after 9/11. Nobody wanted to fly, probably because they're afraid of the risk of flying. The same thing happened with COVID, right? Nobody flew. All right, a travel agent suggests that since the law of averages makes it highly unlikely to have two plane crashes within a few weeks of each other, so flying soon after crash is the safest time. So one plane going down does not impact the likelihood of another plane going down unless they just launched the Boeing 737 MAX. Just kidding. That was mean. Anyway, what are you going to do? So they're independent events. So if one happens, that doesn't mean that, oh, well, then we're, the likelihood of having another one happens. No, it's exactly the same. So the response to this is that the law of averages is not true. So most people won't say it's a law of averages, but we know it's not true. So we can't predict short-run behavior on the long run. All right, if an airline industry proudly announces that it has set a new record for the longest period of safe flights, would you be reluctant to fly? Does it mean they're due to have a crash? Again, that's the same issue. No, we don't know what's going to happen. We know in the long run it'll settle down, but we don't know when they're going to have the next crash. I mean, if we knew that, then we just wouldn't fly on that day, right? Again, it's like extrapolation. We don't know what's going to happen in the short run, but in the long run, we do know the big averages. And that's how we do insurance. All right, so our first rule is that the probabilities must strictly between 0 and 1 for any event. The second rule is that the assignments of the probabilities of the sample space must all add up to 1. So if we have everything possible outcome and their individual probabilities, they must add up to 1. Then the complement rule. So the probability of it occurring is 1 minus the probability of the event that it doesn't occur. So if the probability of getting green light is 35%, the probability of not getting green light has to be 65%. Is 1 minus the 35, because if those are the two possible ones, it either happened or it didn't happen, and there could be other combinations of it not happening, like yellow that we treated as green, yellow that we treated as red, etc., etc. But overall, they would add to the 65%. All right, so there's a good hint here. Anytime you're calculating the probability of several events, like the probability of out of three rolls, at least one of them is a 6. The at least 1 6 means that you could have 1 6, you could have 2 6s, or 3 6s. Now we can find the probability of all three of those events occurring and add them all up, and that would be it. But the best way to do this, anytime you see at least 1, is we should find the complement and subtract it from 1. So what's the probability that out of 3 rolls we don't get a 6? Well, that's going to be the probability of the first roll of not getting 6. There's 5 favorable outcomes out of 6 possible outcomes. So 5 favorable or any of them that are 1 through 5 that are not a 6. And so that's 5, 6. Then the second rule is independent, so it's not like we're drawing without replacement, so it's still going to be 5, 6, and then we have 5, 6 on the last one. We multiply all those together, it's 5, 6 to the third power, and then we're going to subtract that from 1. That's finding the complement. So the complement can actually be shown here as well. So if event A happens, and if we want to know the sum of all the possible combinations of things that are not A, we would just take 1 minus the probability of A happening, and that'll give us all the shaded region. The complement is also shown with this superscript C up here for the complement. Other textbooks might have something else with like a bar or a not symbol or tilde or whatever, but we're just going to use the capital C in a superscript for the complement. So 1 minus the probability of, so the probability of having at least 1 6 could be 1 6 plus 2 6s or 3 6s. But the best way to do it, instead of finding all those individual probabilities, is to do 1 minus the probability that it doesn't occur, which is 5, 6 to the third power, which gives us this number, which ends up being about 42% chance. All right, so many stores run secret sales. Shoppers receive a scratch-off ticket at checkout to determine their discount. The store is required to reveal in the fine print the distribution of the discounts available. Which of the probability assignments are legit or could be legit? So here's their sample space. These are all the possible outcomes of discounts you can get. And remember, they have to add up to this. Some of the probabilities of the sample space has to add up to 1. So 20%, 20%, 20%, 20%. That's up 80%. That's not possible. So that's not legit. Clearly something's wrong. They are probably, if they're all equal, then it would actually be 25% because there's a fourth of them each. This is going to be 1.1. So if we add all these up together, or sorry, the sum of that's going to be equal to 1.1, which that's not 1. That's not going to work. Here, those all add up, so that's legit. This one is not legit because you can't have a negative probability. So even though these would add to 1, you can't have less than 0. So that's not legit. And this one's legit as well. It's just, wow, that's boring. If everyone got 10%. All right. Number 1, sample spaces. And again, this is not a problem, so you can check it on the back of the book. All right. Record all the possible outcomes, and then just if you think they're equally as likely. Toss 2 coins, the order of the heads. So if the order matters, then we have 4 different outcomes for their orders. And each one of those with the orders are equally as likely, right? It's 50. They're all going to be 25% chance. We talked about that. Now, if we weren't looking at the order of heads and tails, but the number of heads out of 2 coin flips, then it would be adding these 2 together, which would make it where that would be having 1 head and 1 tail would be the most likely, twice as likely to occur as having 2 heads or 2 tails. Family has 3 children. Record the number of boys. So they could have 0 all the way up to 3 boys. 4? That's not right. Anyway, 0 up to 3. And the most likely, because we're not talking about order here, the orders would be equally as likely, and there'd be lots of those. It'd be a permutation. Anyway, so out of 3, choose 3. Could be right. Anyway, 3, choose 1, 3, choose 0, all that stuff. Anyway, on this one, the middle one's, of course, going to be the most common. Flip a coin until you get a head or 3 consecutive tails. Okay, so we could... So flip until you get a head, or if you get 3 tails, then you're done. So the most we're ever going to flip is 3 times, but we could flip shorter than that if we got heads. So we could get a heads on the first and we're done. We could get a tails then a head. We could get 2 tails then a head, or we can get 3 tails and we're done. So there's really only 4 outcomes there because we're stopping after the third one, and we either flip till we got a head or till we got 3 tails. Then we were done with it. Are they all as likely? No, because this is a 50% chance, and that would be 50% times 50%, and then 50% times 50% times 50%. The last 2 are equally as likely, but because we're adding an additional independent event, the probability for after each one is going to be half of the one before. So, all right, roll the dice, record the larger number. So the largest number of 2 dice could be 1, and always could go all the way up to 6. And really, between the two, the probabilities of these occurring... Yeah, that's not actually going to be equally as likely, because to have the highest number of 1 means both of them must have been a 1. But to have the highest number of 2, you could have 2 2s or a 2 and a 1, and you would still just record the highest number. So as we get closer to the right, there's more possible combinations for the other one to have occurred. So this is interesting because this is not, it's not like a bell-shaped curve. It's actually going to be skewed to the left in this case. That's kind of a cool one. All right, roulette. Casino claims that its roulette wheel is truly random. What should the claim mean? So again, if you remember random, we know what can happen, but nobody knows what will happen. So also there's usually an assumption that they're equally as likely, at least if the areas on the wheel are the same. But of course, the rarer ones are going to be the ones that pay out better. All right, we know what can happen, but no one knows what will happen. So there are 3 different types of probability. Personal, which is like a gut feeling. I never do that. You always say that. Stuff like that. It's kind of funny. Quantifiers get you in trouble, and especially legally speaking. And then empirical and theoretical. So theoretical probability is based on like cards or dice. If we know it's like a controlled environment, we know like what's the probability of drawing an ace out of a full deck of cards? Well, it's 1 out of 13, right? Yeah, it's 13. Yeah, so 1 out of 13 would be the probability of drawing an ace. And then once you draw an ace, it's the probability of drawing another ace. Well, we can figure that out because it's a controlled environment. We know there's like a finite set of things that could happen. And so that would be theoretical probability. And we'll deal with that quite a bit in this course. But the empirical probability is based on a random phenomenon, like the probability of, not rolling a dice or anything, but of like the light example, like getting a green light, some random phenomenon that we don't know what the actual probability is. The only way to really figure it out is through a simulation. And then just in the long run, it will approach it if it's actually independent. So the weather reporter makes the predictions of a 25% chance of rain. What kind of probability is it? So he is basing it on like, what's going on in other places and how fast the front's moving and stuff like that. But it's not something that can be tested again. So it's not like we go in the DeLorean, go back in time, and then try it again. That doesn't even make sense. Like it either happened or it didn't happen. It's not going to change anything like that. So this is not going to be empirical probability. It's not a random event that occurs every day. It's not theoretical because it's not like a controlled environment. We know all the possible outcomes and they're all equally as likely or anything like that. So this is what we call personal probability. So it's based on a personal degree of certainty. So that weatherman, if he had to put a number to it, and he did, he's subjectively saying he believes at 25% chance of rain tomorrow. Yeah. All right. Winter. Comment on the following quotation. I think it's our best determination it'll be colder than normal winter, said someone, a Wisconsin State climatologist. I'm basing that on a couple different things. First, I look at the past few winters, and there's been a lack of really cold weather. Although we're not supposed to use the laws of averages, we are due. Okay, so again, we're not due for anything. You in the long run, we might be able to say something about the behavior, but in the short run, we don't know what's going to happen. It's like oil prices. They've been going down forever, so are they going to keep going down, or are they going to go back up? We don't. Eventually, they'll probably go back up, but we don't know when. Could happen now, 5 years, 10 years, 100 years, never. Well, probably not, never. Never say never. Anyway, so short run, we don't know. Long run behavior, that's where we get into empirical probability. All right, that's it. Sorry, I went a little bit long. Usually whenever I'm starting a unit, I got a lot of vocab that I have to get through, so it's going to be a little bit longer. But we actually only have 3 assignments this week, so it's kind of nice. I'll see you guys later. Have a good day.